Any doubt? Because the training input xi is a random variable, right? Remember, training example are sampled from some underlying data distribution, right? Right? So if you collect the training data this time, you actually got samples from the data distribution D, right? And if you collect another set of training examples, they're different, although they are also sampled from the same data distribution. So the training example itself is a random variable. And this indicator, this binary variable, essentially is a function of those training examples, right? So this indicator is binary as well. So that's why we can view the training error as an average of those RID binary random variables. Why they are independent? Because you're assuming each training examples are sampled independently from the data distribution. Right? So now, if you look at the definition of the generalization error, it is actually the probability that for any example sampled from this data distribution D, your prediction is different from your ground truth label, right? So this is actually, you can view as, okay, when I toss a coin, right? What is the probability you see the head up? You see the head up, right? So if you view this as a binary random variable, this probability is essentially the binary variable takes 1, right? And remember, xi and x, they are all sampled from the data distribution D. They have the same distribution. In other words, this true error is essentially the expectation of each binary variable used in calculating the training error. Does it make sense? Right? Any question? It just follows definition. Right? The true error is a chance that you make a wrong prediction, right? And this chance is essentially the expectation that your binary variable. This binary variable means it's 1 meaning that you make a wrong prediction. It's 0 meaning that you make a correct prediction. So for any binary variable, its expectation or its mean is equal to the probability that binary variable is 1, right? And now looking at the definition of the training error, you see that we simply average the set of binary indicator random variables, right? This is essentially an empirical estimate of the true error. Any question? Everyone's good? Okay, great. So now, if you want to know what is the probability that the true error is, say, more than epsilon away from the empirical error, we can apply the Hopkins inequality directly. Okay? So here, the true mean now is the true error, right? The generalization error. And the empirical estimate of the mean, or empirical mean, is now replaced by the training error, right? So this is just a straightforward application, because the training error is an empirical estimate of the true error. So apply Hopkins inequality, we immediately get this result. So now, we got our first important conclusion about the agnostic learning. For any specific hypothesis H, we know that the true error of H is more than epsilon away from the training error, is bounded above by this exponential term. This is done by applying Hopkins inequality directly without any change. And now we should extend it to a more general case, right? Because our learning is conducting a search over the hypothesis space, right? We actually do not know which particular hypothesis is going to be selected before the training procedure, right? So similar to what we have done for the consistent learning, we want to make a more general statement about this chance, meaning that we want to know what is the probability that there exists a hypothesis in a hypothesis space such that its true error is epsilon away from the